everyone, today we will learn the working principle of PID controllers. PID performs proportional integral and differential operations on the input deviation and apply the superposition result of the operations to the executing mechanism. P represents integration, I represents integration, and D represents differentiation. The description of PID is simple. However, PID controllers are applied to various fields, from the so-called control to the successful launch of the Shenzhou 7 launch, from air conditioning and wind control to missile guidance, from energy and chemical industry to environmental friendly household appliances, from manufacturing and processing to aerospace, and so on. Nowadays, from daily life to factories, PID controllers are applied and play significant roles everywhere. The PID controller has a history of nearly 100 years since its inception. It has become one of the main technologies in industrial control due to its simple structure, high stability, reliable operation, and easy adjustment. Firstly, let's take a look at the PID control diagram. Industrial production often requires closed-loop control to achieve continuous analog control of temperature, pressure, flow rate, and other variables. Whether using analog controllers, analog control systems, or computers including digital control systems of PLC, PID has been extensively applied. As shown in the figure, it is a PID control diagram of variable frequency constant pressure water supply pressure control. In this diagram, target value is also called set point value. For example, the water supply pressure is set to be 0.4 megapascal. Process value is also called actual value. For example, the deviation of the actual water pressure in the water supply pipe is the difference between the target value and the process value. This difference is sent to the PID calculation unit, processed, and output to drive the actuator, such as a frequency converter. Here, this actuator is either an electric motor or a frequency converter, and the controlled object is pressure. The transmitter converts pressure into electricity and feeds it back to the input terminal. The system takes the water pressure in pipe network as the set parameter, and controls output frequency of the frequency converter through PLC to automatically adjust the speed of the water pump motor, achieving PID closed-loop regulation of water pressure. Set point pressure, SP, for the water supply system. As the water consumption increases, the pressure in the pipe decreases. After the transmitter converts and outputs process value, PV will also decrease. When the process value, PV, is compared with set point value, the deviation will increase. Through PID calculation, the frequency of the output control frequency converter and the speed of the water pump will increase. The water supply will correspondingly increase, and the water pressure in the pipeline network will increase. The water supply pressure has also started to rise, returning to the target value, maintaining the pressure constant, and the system is equilibrium. When the water consumption decreases, the frequency decreases, the pump speed slows down, and the water supply decreases. Constant pressure water supply is essentially to meet the requirements of water flow rate. As the size of water pressure in the water supply pipe, water supply capacity, and water demand are ultimately reflected in changes in water pressure. Water pressure is usually used to indirectly control the magnitude of water flow. As long as the pressure on the water supply pipe stays unchanged, the balance between the water supply flow and the water consumption flow in the pipe is ensured, thus achieving the goal of constant pressure water supply. Here is the basic formula for PID: Kp, proportional coefficient, T, integral time constant, Td, derivative time constant, E, T deviation. In practice, PID operation requires periodic data acquisition, so the above formula needs to be discretized. The discretization formula for PID algorithm is as below. The regulating role of each unit in PID is as below. 1. Proportional unit, P. This is the deviation signal of the proportional reaction control system. Once the deviation occurs, the regulator immediately exerts control to reduce it. 2. Integral unit, I. Mainly used to eliminate static errors and improve the accuracy of the system. The strength of the integration effect depends on the integration time constant T. The larger T, the weaker the integration effect, and vice versa. 3. Derivative unit, D. It can reflect the trend of deviation signals and introduce an effective early correction signal into the system before the value of the deviation signal increases, which can overcome inertia lag and accelerate action time. This completes the lesson. See you next time.